In this video, we're going to start to explore systems of linear equations. We're going to study systems all of this week using algebraic methods. Next week, we're going to look at systems again using matrices. So a system of linear equations is simply two or more linear equations. And of course, we could have a system of nonlinear equations as well. In this case, we know that they're a system because of the bracket. The bracket tells us it's a system. And the fact that we have these that are linear, remember linear forms that we're used to are standard form, which looks like this, and slope-intercept form that looks like this. So obviously these are both written in standard form, but we might see them in slope-intercept form. We might have a vertical line, we might have a horizontal line. You get the idea. Any of these could be part of our system. The purpose of a system, or what we'll be interested in, typically is a solution, which is where both equations or all of the equations within the system are true. So graphically, that would be the point at which they cross, or algebraically, it would be the point at which I could plug those values in and get a true statement for each of the equations. So here's a fantastic example that is pretty simple because there's only two equations and obviously they're linear because it's a straight line. And it relates the number of miles traveled to the total cost of the trip using two different cab companies. So what we would be looking at, typically what we first look at is this point right here, 3, 8. So I can see here on my graph the point 3, 8 is the point at which the two lines cross. This is called the solution. So mathematically, if I said solve the system, you would solve to find 3, 8 and then be done. If it's a story problem, typically we want to know what does that point mean? Well, that point, because x is the number of miles, that would be 3 miles, and y is the total cost, we're assuming in dollars, so that would be $8. So what does that point mean? That point means if my trip is 3 miles, that it would cost $8 with either cab company. So then that brings up what happens before 3 miles, so in the interval from 0 to 3, but not including 3, which would be from here to here on my graph, what's happening? Well, I can see that blue would be more expensive, and so yellow would be the cheaper option. So I'm just going to put yellow cheaper, because if I were going to travel less than 3 miles, then I would certainly choose the yellow cab. In the interval from 3 to infinity, which means from here on out, now what? Well, I can see that the cheaper option, because it's below the other line, the cheaper option is the blue cab. So blue is cheaper. So again, why does that matter? Because at the break-even point, which is here, the solution, sometimes called the break-even point, is where both would be exactly the same cost. Typically before that, one will be cheaper, and after that, the other will be cheaper. So when we're dealing with just two lines, which is where we'll start, we are going to have three different possibilities. Those possibilities are, like we just looked at, that our two lines cross at exactly one point, and that point is the solution to our system. So this number of solutions is just one, and that solution is the point where those two lines intersect. This is called a consistent solution because there's one or more solutions. And it's called independent because both of those lines are different. It's also possible that we have two lines that never intersect because they're parallel. And if they never intersect, that means they have no solutions, because obviously a solution is where they intersect. This is called an inconsistent system because it has no solutions. The third type of system that you might see is, and it's really hard to tell, but there are two lines here. They're just stacked on top of one another. And so because those cross at every single point on the line, there are infinitely many solutions. Infinitely many because every time they cross it's a solution and they cross everywhere. And so the solution set is the set of all points on the line, or the equation of the line, etc. It's still considered consistent, just like up here, because there is a solution, but this is called dependent because it's essentially the same line twice. In our next video, we'll explore some of the ways that we can solve a system. Here, we're just asked to verify whether or not something is a solution. So to do that, essentially, I'm going to take my first equation, and I'm going to replace x with -4, and I'm going to replace y with 16, and I'm going to verify that those two sides equal. -4 times -4 is 16, so it works. And because it works for the first one, I will check the second one. So now I'm using my second equation in the system, replacing y with 16, replacing x with -4, and I get 16 equals 8 plus 8, and 16 equals 16, and so they work out. So because both sides equal in both equations, then it is true that -4, 16 is a solution to the system. So here are two for you to try. Keep in mind that if you plug it into the first one and it doesn't work, don't even bother plugging it into the second one because it doesn't matter. So press pause, try this question, then press play to see how you did. So looking at the first one, I'm looking at 3, -1, and so I'm replacing y with -1 and x with 3, and I get -1 equals 6 minus 8. 6 minus 8 is -2. Those two things don't equal, and that means I'm not even going to check this one because it doesn't work for the first one, so I honestly don't care if it works for the second one. So that would be a big fat no on our first example. On our second example, I would replace y with -1. I would replace x with 3, and then simplify. -2 times 3, -6. -6 plus 5 is -1, so it checks out for the first equation. Because it checked out for the first equation, I'll check the second equation. -1 equals 3 minus 4, and then 3 minus 4 is -1, and so it worked for both, and so my answer is yes.